Welcome to today's paper reading. Today's paper is titled, Flatness-aware Sequential Learning Generates Resilient Backdoors. This paper was published on AR14 by Hoang Pham and colleagues from Vinh University, Cyros Data 61, and Vinh.AI Research. The abstract highlights the growing concern of backdoor attacks on machine learning models. These attacks aim to be resistant to defensive algorithms, yet some fine-tuning defenses have shown notable efficacy in removing them. This effectiveness is largely due to the catastrophic forgetting (CF) property of deep neural networks. To counter this, the paper leverages continual learning (CL) techniques. It begins by analyzing the connectivity between a backdoored and fine-tuned model in the loss landscape, confirming that fine-tuning can push the model out of backdoor regions. Based on this, the paper reformulates backdoor training through the lens of CL, proposing a novel framework called sequential backdoor learning (SBL) to generate resilient backdoors. This framework separates the poisoning process into two tasks, with the second task moving the model to a backdoored region resistant to fine-tuning. Additionally, the framework seeks flatter backdoor regions via a sharpness-aware minimizer, enhancing the durability of the implanted backdoor. Extensive empirical experiments on benchmark datasets demonstrate the effectiveness of the proposed method. The rapid advancements in machine learning, particularly in deep neural networks, have significantly impacted various fields from computer vision to natural language processing. However, these well-trained models, which are valuable due to the resources invested in them, have become targets for cyber attacks. Prior studies have shown that DNN models are susceptible to various attacks, including adversarial, poisoning, and backdoor attacks. Backdoor attacks, in particular, involve injecting a hidden backdoor into the model, either by contaminating the training data or manipulating the training process. This backdoored model behaves normally until a specific trigger is detected, at which point it produces an output defined by the attacker. This can lead to harmful consequences when the poisoned model is integrated into systems. Figure 1 illustrates the differences in the effectiveness of fine-tuning defenses against conventional backdoor learning (CBL) and the proposed sequential backdoor learning (SBL) framework. In Part A, the backdoored model θB is shown being pushed out of the backdoor region (red area) by fine-tuning, which is the intuition behind the success of fine-tuning defenses against CBL. Conversely, Part C demonstrates how the SBL framework traps θB within a backdoor region that is resistant to fine-tuning, making it difficult for defenses to remove the backdoor. Parts B and D provide visualizations of the loss and accuracy on clean and poison test sets for intermediate models when linearly interpolating between backdoored and fine-tuned models, comparing the outcomes of CBL and SBL. These visualizations highlight the resilience of the backdoor in the SBL framework compared to the vulnerability in CBL. In backdoor attacks, the adversary aims to manipulate the model's output to a specific target label using predefined triggers. The injection process can be done by poisoning data or maliciously implanting a backdoor during training. Various backdoor attacks focus on designing different triggers. Backdoor defenses are categorized into pre-training, in-training, and post-training stages. Post-training defenses are common due to the difficulty of altering the training process. These defenses include fine-tuning and pruning methods. Continual learning addresses the challenge of preserving previous knowledge while learning new tasks. This paper views backdoor attack and defense as a continual learning problem. In the backdoor attack setting, the attacker trains a model and provides it to the victim, which opens up opportunities for training control backdoor attacks. The attacker's goal is to implant a backdoor into the model and bypass post-training defense methods, especially fine-tuning defenses. The defender's goal is to fine-tune the model on clean data to remove potentially hidden backdoors while maintaining the model's performance on their data. Figure 2 illustrates the loss and accuracy on clean and poison test sets of intermediate models during linear interpolation between models. The first column shows the interpolation between backdoored and fine-tuned models in conventional backdoor learning (CBL). The clean loss and accuracy remain unchanged, while the poisoning loss increases and the attack success rate (ASR) decreases to nearly zero on the fine-tuned model. This indicates that fine-tuning can effectively push the poisoned model out of the backdoor affected area in CBL. The second column compares models in the first, θB0, and second task, θB, within the SBL framework. The third column shows the interpolation between backdoored and fine-tuned models in the SBL framework. The persistently high ASR and low poisoning losses demonstrate that SBL can trap the backdoored model in a backdoored region that is difficult to escape from, even after fine-tuning defenses. Figure 3 illustrates the gradient norm comparison between conventional backdoor learning, CBL, and our sequential backdoor learning, SBL, framework during the defense fine-tuning process using SGD 0.01 from the backdoored model. The key observation is that in the early stages of fine-tuning, the gradient norm values of CBL are substantially higher than those of SBL. This suggests that the fine-tuned model from CBL can more easily be pushed further away from the backdoored minimum, making it easier for the fine-tuning defenses to find backdoor-free local minima. In contrast, SBL maintains lower gradient norms, indicating a more stable and resistant model to backdoor forgetting. The experiments were conducted using 3 benchmark datasets, CIFAR-10, GTSRB, and ImageNet-10. The models used include ResNet-18, VGG-16, and ResNet-20. Representative backdoor attacks considered in the experiments include badnets, blended, and SIG. For badnets, a random color, 3x3 square at the bottom right corner was used as the backdoor trigger on all datasets. The persistence of the backdoored models was evaluated against fine-tuning-based defenses, including standard fine-tuning, SAM-FT, and NAD. The performance of the backdoored models was assessed using clean accuracy, CA, and attack success rate, ASR. The results show that SBL significantly enhances the backdoor's resilience against all the previously mentioned defensive methods. A qualitative analysis of SBL's effectiveness was conducted by examining the gradient's norm during the fine-tuning process. Table 1 presents the resilience of backdoored models trained with sequential backdoor learning, SBL, against various fine-tuning defenses on the CIFAR-10 dataset using ResNet-18. The table compares the performance of SBL models trained with different continual learning, CL, techniques against conventional backdoor training methods. Key metrics such as clean accuracy, CA, and attack success rate, ASR, are used to evaluate the effectiveness of the defenses. The results show that SBL significantly enhances the resilience of backdoored models against fine-tuning, maintaining high CA while preserving ASR, which is not the case with conventional backdoor training methods. This improvement is attributed to the flat minima discovered by SBL, which makes the backdoors more resistant to fine-tuning-based defenses. Table 2 presents the resilience of ResNet-18 on GTSRB against various fine-tuning defenses. The table compares the performance of SBL, sequential learning with backdoors, using different methods, naive, EWC, AGM, against multiple attack types, bayonets, blended, SIG, dynamic. The key metrics include classification accuracy, CA, and attack success rate, ASR. The data indicates that SBL methods generally maintain high resilience, with SBLW, EWC and SBLW, AGM showing particularly strong performance across different attacks and fine-tuning defenses. Table 3 presents the resilience of fine-tuning defenses in the context of ResNet-18 on the ImageNet-10 dataset. The table details the performance metrics under various attack scenarios, including badnets, blended, and SIG. Key metrics such as classification accuracy, CA, and attack success rate, ASR, are provided for different fine-tuning strategies, including SGD with learning rates of 0.005 and 0.01. The data highlights the effectiveness of different defense mechanisms, such as naive, EWC, and AGM, in mitigating the impact of adversarial attacks during the fine-tuning process. Table 4 presents an ablation study on various architectures using the CIFAR-10 dataset. The study evaluates the performance of different architectures, including ResNet-18 and VGG-16, under various defense mechanisms such as no defense, SBL, shaping the backdoor loss, FTSGD 0.01, fine-tuning with stochastic gradient descent at a learning rate of 0.01, NAD, neural attention distillation, and FT-SAM. Fine-tuning with sharpness-aware minimization. The metrics assessed include attack success rate, ASR, and clean accuracy, CA. The results indicate the effectiveness of each defense mechanism in mitigating the impact of adversarial attacks across different architectures. Table 5 presents an ablation study on various neural network architectures using the GTSRB dataset. The architectures evaluated include BADNets, blended, and SIG. The study examines the effectiveness of different defense methods: no defense, SBL, structured backdoor learning, FTSGD 0.01, fine-tuning with stochastic gradient descent at 0.01 learning rate, NAD, neural attention distillation, and FTSAM, fine-tuning with sharpness-aware minimization. Key metrics analyzed are the attack success rate, ASR, and clean accuracy, CA. The results highlight the performance of each architecture under different defense strategies, providing insights into their robustness against backdoor attacks. Table 6 presents an ablation study focusing on the role of continual learning, CL, techniques with the BADNets model. The study evaluates the effectiveness of different CL methods including naive, EWC, anchoring, and AGM, without the use of sharpness-aware minimizer, SAM. The results are categorized by training steps and show the performance metrics for attack success rate, ASR, and clean accuracy, CA, under various fine-tuning scenarios such as FTSGD with different learning rates and NAD. Additionally, the table includes data for FTSAM, highlighting the impact of SAM on backdoor persistence. The findings indicate that CL techniques significantly enhance the model's resistance to backdoor attacks during fine-tuning, with FTSAM demonstrating particularly effective mitigation of backdoor persistence. Table 7 presents an ablation study focusing on the role of SAM, sharpness-aware minimization, in conjunction with ResNet 18 models on the SAFAR 10 dataset. The study evaluates the effectiveness of SAM in enhancing the durability of backdoored models under various training conditions and defenses. Key metrics analyzed include attack success rate, ASR, and clean accuracy, CA. The table highlights the performance differences when SAM is used versus when it is not, particularly in scenarios involving conventional backdoor learning, CBL, and standard backdoor learning, SBL. Additionally, the impact of fine-tuning with stochastic gradient descent, FTSGD, and SAM-based fine-tuning, FTSAM, on these metrics is examined. The results indicate that while SAM can improve backdoor durability in some cases, its consistent effectiveness across different defenses is not guaranteed. Table 8 presents the performance metrics of a backdoored model trained with different learning rates during the second task on SAFAR 10 using ResNet 18. The learning rates examined range from 0.0005 to 0.01, and the model's performance is evaluated using the SBL framework with both naive and EWC methods. Key metrics include attack success rate, ASR, and clean accuracy, CA, for both the initial training step, Step 1, and after fine-tuning with SGD at a learning rate of 0.01, FTSGD 0.01. The data reveals that smaller learning rates in Step 1 allowed the backdoored model to effectively bypass fine-tuning defenses, whereas larger learning rates lead to a significant drop in ASR, akin to fine-tuning defense outcomes. EWC remains effective in preventing backdoor forgetting but at the expense of clean performance. Table 9 presents an ablation study on the poisoning rate, PR, within our sequential backdoor learning, SBL, framework and compares it with the original training method using BADNets. The study evaluates the impact of different poisoning rates, 1% and 5%, on the performance of backdoored models against various defenses. The defenses tested include no defense, standard fine-tuning with SGD, FTSGD 0.01, neural attentive distillation, NAD, and sharpness-aware minimization fine-tuning, FTSAM. The performance metrics used are clean accuracy, CA, and attack success rate, ASR. The results show that SBL significantly enhances the resilience of backdoored models against fine-tuning defenses, even at lower poisoning rates, demonstrating the effectiveness of the SBL framework in mitigating backdoor forgetting and improving the robustness of implanted backdoors. In this paper, The authors introduce a novel backdoor training framework designed to enhance the resilience of implanted backdoors against fine-tuning defenses. This framework divides the backdoor learning process into two distinct steps, employing a sharpness-aware minimizer to trap the model and backdoor regions that are resistant to existing defenses. Extensive experiments on several benchmark datasets have shown the framework's effectiveness compared to traditional backdoor learning methods. The research highlights a significant new threat to fine-tuning defenses and calls for the development of countermeasures to address this type of attack. Thank you for watching.